Welcome to example number 16. Before I start that example, let me first give you a brief introduction of EMF and terminal voltage. So up to this point, we have assumed that our batteries are ideal batteries. We've assumed that the EMF is from this particular source here is really equal to the terminal voltage, which would be from A to B. But really, real sources of EMF don't behave exactly like ideal sources we've described, because the charge, when it moves through the battery source, or any material in fact, it will encounter some internal resistance. Now that internal resistance of the source is denoted by a small letter R. If this resistance behaves according to Ohm's law, where R is constant, then the voltage lost from that particular resistance would be equal to V equals I times R. The terminal potential difference, or terminal voltage, is if we were to hook up a voltmeter from here to here, from A to B, that would be essentially hooking up a voltmeter across the terminals of a battery. So that voltage from A to B is equal to the EMF minus the voltage drop that is lost within the battery. And that is due to the internal resistance of the battery. So it would follow, for example, that I would be equal to the EMF all over R plus little r. Now, because why am I saying that? Because the voltage AB is also equal to I times R. Now that capital R in this case is often called the load resistance. That's the total equivalent resistance that is outside of the battery. So if you equate these two, you'll get the current is equal to the EMF divided by the equivalent resistance or load resistance plus the internal resistance. So looking at the graph to the right, this shows you just a schematic diagram of what happens to the potential changes over a particular cycle. So if we start here at A, and we assume at A that potential is 0, and it grows across the EMF, it'll pump up to, say, let's just give an example, say 6 volts. And then there will be some voltage drop within the battery. So let's say that is a 0.1 volt potential drop. So therefore now, outside of the terminals, when it gets to B, we now have 5.9 volts available for the rest of the circuit. And then as that charge flows from B all the way back to the negative terminal of the battery at A, it will lose the remaining 0.9 volts here when you get to D. And then this cycle would then repeat itself once more like this and continue going onwards and onwards and onwards. And we can also discuss the power over the different components of the circuit. So the total power of the circuit would be represented from the power externally dissipated during the external part of the circuit. So this load resistance R multiplied by the current squared. And then this term right here, I squared times little r, is the power dissipated within the battery itself from the internal resistance. If you pick up the battery over a period of time, you'll notice that it will be warm, and that's this energy per unit time that's being lost. And this total power is equal to I times the total EMF. Okay, now let's see an application of this in example number 16. We have a battery that has a total EMF of 12 volts. That means it has 12 joules of energy that it can provide for every coulomb of charge that flows through it. Inside that battery, there is an internal resistance, as you can see here, and we'll label that little r, and that's equal to 0.05 ohms. Outside of the circuit, it's hooked up to something like a motor or whatnot, and so that external resistance R is 3 ohms. So we call that the load resistance. We're asked in part A to find the total net current that is flowing through the circuit and the terminal voltage of the battery. So part A is what is I and what is the voltage over the terminal. So we're going to label that AB. So here is the positive terminal. We'll call that A, and then B over here is the negative terminal. So how much is lost, or what is the voltage across the terminals? So, and then in part B, we're looking for the power that is dissipated over the load resistance. So that would be externally. And then we want the power delivered by the battery itself, so that would be the total power. And why don't we just also find the power delivered the power or the energy per unit time that is dissipated from within the battery, so from the internal resistance. So our solution here now is we're going to try to find the total current. And you can apply Ohm's law. The total EMF would be equal to the current times the total resistance. Now, the total resistance is not just the load resistance. You now have to realize that it would be R plus also this internal resistance. These two resistors are in series. That's why I'm adding them in this way. So we have then 12 volts equals that current, and the load resistance is 3 ohms plus 0.05 ohms. And you can go ahead and put that into your calculator. That would be 12 volts divided by 3.05 ohms. And that's going to give you 3.93 amps. Now let's see how much of that terminal voltage is available. We know that there's 12 volts totally available of energy per coulomb, but we're not going to get 12 volts. We should get something slightly less than that. So the terminal voltage would be that EMF minus the voltage drop lost within the battery. So that would be 12 volts minus the internal that current times the internal resistance. That's 3.93 amps times 0.05 ohms. So go ahead and put that onto your calculator, and you'll get 11.8 volts. And you'll notice, by the way, this terminal voltage is not going to be constant. The higher the current, then the more that potential drop is going to be lost within the battery, and the less you'll get available outside. And the higher current will depend on what that load resistance out here is. So if R gets smaller and smaller and smaller, that load resistance, then the current that's driven through the circuit is going to get larger, and so there'll be less voltage available externally on the terminals. So now we're ready to go on to part B and find out what is the power dissipated in each of the different categories here. We have the power over the load resistor, so that would be I squared times R. That's 3.93 amps squared times the load resistance, which is 3 ohms. We have the power over the internal resistance, that would be I squared times the internal resistance, that's 3.93 amps squared times 0.05 ohms. And we have the total power, which is basically, we could use I times the total voltage, which is the EMF, and that would be 3.93 amps times total voltage is 12 volts. You could do it another way also. You could do I squared times the total resistance. So if you go ahead and input these numbers into your calculator, and you'll see you'll get externally 46.4 watts. Internally in the battery, that's that heat generated inside the battery, 0.774 watts. And then if you look at these two, they should add up to the total power, which is 47.2. And just a quick reflection, when you talk about old batteries versus new batteries, one of the big differences between an old battery and a new battery is that as time progresses, that internal resistance within the battery would go from, say, a few ohms to almost as much as 1,000 ohms over a long use. And it's also true, too, if you think of batteries in the colder countries, like, say, Canada, in the cold mornings, a battery would basically provide less current in that cold morning, and that's because the internal resistance will increase with a colder temperature. So as the temperature outside drops, that internal resistance inside the battery will increase, and then that will provide less current from that battery. So a lot of times you'll have people in the colder countries that will tend to warm up their batteries. One way you'll get some places they'll even soak up their batteries in warm water to try to keep it warm so that you can have a higher current from that battery. And that's it for example number 16.